Previously, we explained that the probability model is nonlinear. Therefore, you cannot use the least squares approach to estimate the coefficients in this model. To figure out how to estimate the betas, we need to get a sense on the sampling distribution of the estimators. We briefly mentioned before that you can still perform the standard inference tests on the probability estimators. In this section, we'll explain why that is the case. The linear regression models are estimated using the least squares approach by minimizing the sum of squared residuals. Let's see if we can use the same approach to estimate the probability model. The regression residual of the probability model is given by y minus phi, which is the standard normal CDF function, evaluated at beta naught plus beta 1 times x. We call this the nonlinear least squares estimation. If you try to solve this problem algebraically, you will see that it doesn't have a closed form solution. The only way to solve this problem is by employing numerical methods, fitting different values to the x variable, and through a trial and error process, find the minimum of this nonlinear function. By the end of it, you will see that the estimators obtained in this nonlinear least squares estimation are not efficient. In other words, these estimators have large standard errors. To calculate more efficient estimators, we need to use the maximum likelihood estimators, or MLE. What is the MLE? To compute the MLE, we have to first compute the likelihood function, which is a conditional density of y's given x's. You can think of the likelihood function as a conditional probability function. The parameters in these likelihood functions are beta naught and beta 1. The maximum likelihood estimators, or MLE, are the values of beta naught and beta 1s that maximize the log of the likelihood function. In this capacity, you can think of the MLE estimators as the beta naught and beta 1 most likely to have produced the data, because now the likelihood function is maximized. In large samples, MLE is unbiased and consistent, normally distributed and efficient. Unbiased means that the expected value of MLE is equal to the true MLE. Consistent means that as the sample size increases, the estimated standard error for the coefficients becomes smaller. And efficient means that the standard error of the MLE is the smallest among all estimators. Because the MLEs are normally distributed, we can perform the standard inference tests such as f-test and t-test on the MLEs. Let's look at a simple example to see how MLEs are estimated. In this example, we're looking at a probability model with no covariates, where no x's, only one y. You can think of y as the result of a coin toss. If a coin lands on the head, then y is equal to 1 with the probability of p. If a coin lands on the tail, then y is equal to 0 with the probability of 1 minus p. If p is equal to 50%, then it's a fair coin toss. If p is not equal to 50%, then it's not a fair coin toss. If you toss a coin many times, the outcome of the coin toss follows a Bernoulli distribution. Formally, we can write the probability of each coin toss using this function. P to the power of y times 1 minus p to the power of 1 minus y. If the coin lands on the head, yi is equal to 1, the probability is therefore given by p to the power of 1 times 1 minus p to the power of 0, or just p. If the coin lands on the tail, yi is equal to 0, the probability is hence p to the power of 0 times 1 minus p to the power of 1, or equals to 1 minus p. If we toss the coin many times, the probability of that particular outcome can be calculated using the likelihood function. The likelihood function is essentially the joint density function with p as the parameter in this case. Let me demonstrate to you how to compute the likelihood function. In this example, I tossed a coin 5 times. The first toss lands on the head, and therefore the probability that this event happens is given by p to the power of 1 times 1 minus p to the power of 0. The second coin toss lands on the tail, and hence the probability that this event happens is given by p to the power of 0 times 1 minus p to the power of 1, and so on and so forth. In the end, the likelihood function of these 5 events is given by the joint density function, which is obtained by multiplying the individual probability of the 5 events together. Since there are 3 heads and 2 tails, the likelihood function is given by p to the power of 3, representing the 3 heads, times 1 minus p to the power of 2, representing the 2 tails. The MLEs are the parameters that maximize the log of the likelihood function. In this case, since there is only one parameter, p, the MLE is the p that maximizes the log of the likelihood function, given here. With some calculation, I can show you that the MLE is equal to the average y, which is a number that is a fraction of 1. In the demonstration problem, for example, the MLE for p is equal to 3/5, since there are 3 heads in the 5 coin tosses. In the case of a probit model, the likelihood function is obtained by replacing p with phi, estimated at beta naught plus beta 1 times x, like this equation here. The probit MLEs are the parameters that maximize the log of this likelihood function. For the logit model, we'll replace the CDF of the standard normal distribution with the CDF of a logistic regression in the likelihood function to solve for the logit MLE. The computation of MLE is handled using numerical method. Of course, we can use R to do the computation for us using the GLM function, so we don't have to do this by hand. Once you have obtained the MLE, you will see that they have all the nice properties here. They are unbiased, consistent, normally distributed, efficient, and we can do testing on these MLEs, and we don't have to worry about heteroscedasticity problem anymore.